If you haven't already done so, please print this handout and follow along. When we talk about yield, we're talking about the amount of the product that's actually produced when a reaction is carried out. And there's two ways of looking at yield. There's the theoretical yield, which is the amount of product that we would predict using stoichiometry, and the actual yield, which is the amount that's actually produced when you're doing an experiment. So often, the theoretical yield and the actual yield are not the same. And there's a lot of factors. You could have impure reactants, you could have experimental errors, collection errors, competing reactions. These are all different things that could be going on when you're doing a reaction that you don't know about or that you're not aware of that will change your yield. You'll either produce less than you would expect, or you might get results that looks like you're producing more product than you would expect. So there's lots of different errors that can happen that would account for a different yield. And one way that we can measure this difference in yield is something called a percentage yield. So basically it's a comparison of the actual yield compared to the theoretical yield. And I'm going to write a formula that you'll need to know in order to calculate the percentage yield. So to calculate percent yield, you take the actual yield that you get by experiment. This is the actual amount you measure for your product. And you divide that by the theoretical yield, what you would expect to get by stoichiometry. That will give you a decimal number, so you multiply it by 100 to turn it into a percent. It's basically like calculating your mark on a test. You write what you actually got out of what you theoretically could have gotten. So let's do some examples. In the first one, we have 3 grams of oxygen reacting with excess hydrogen to produce water. Now, just a note here, excess hydrogen, it means we have more than enough hydrogen, therefore, our oxygen is the limiting reactant. So we don't need to calculate the limiting reactant here. We already know oxygen is it. Okay, so 2.99 grams of water was produced. So that's the actual yield of water. But we're to find the percentage yield. So this is how I do it. I start by setting up my stoichiometry grid, mass, molar mass, number of moles, fill in the values that I know. I know I'm starting with 3 grams of oxygen, so I'm going to use stoichiometry to figure out how many grams of water I'm expecting to produce. So first step, find the number of moles of oxygen that you're reacting. So I do the math. Mass divided by molar mass gets me 0.0938 moles. So now I look at my ratio. So coefficients are 1 in front of the oxygen, 2 in front of the water. So if I compare moles of oxygen to moles of water, there's twice as many moles of water. So I'll take my moles of oxygen, multiply it by 2, which gives me 0.188 moles of water. The molar mass of water is 18.02 grams per mole, so now I do moles multiplied by molar mass to get an expected mass of 3.39 grams of water. So that's my theoretical yield. To calculate the percentage yield, I'm just going to use my formula. So the percent yield is actual divided by theoretical. My actual yield is 2.99 grams of water. And my theoretical mass is 3.39 grams. Plug in my numbers, and I get 0.882, which is 88.2%. So what this means is I have produced 88.2% of the value that I was expecting. And again, there could be a lot of reasons why my percent yield is lower than I expected. But you really just have to think about your specific case to find out what you think was the issue. So let's do the last example here. Calcium carbonate can be thermally decomposed to calcium oxide and carbon dioxide. So here's the equation. Calcium carbonate is decomposing into calcium oxide and carbon dioxide. Under certain conditions, this reaction proceeds with a 92.4% yield of calcium oxide. And we're asked how many grams of calcium oxide can the chemist expect to obtain if 12.4 grams of calcium carbonate is heated. So this time, we're heating 12.4 grams of calcium carbonate, knowing that we have a percent yield of 92.4%. How much calcium oxide are we going to get? So this time we are trying to find the actual yield. So I set up my stoichiometry grid, mass, molar mass, number of moles. I have 12.4 grams of calcium carbonate. Fill in my molar masses. I'm trying to find the mass of calcium oxide. So I'm still going to start by finding my theoretical yield of calcium oxide. So if you do the math, you'll get 0.124 moles of calcium carbonate. Look at the coefficient. There's a 1 and a 1. It's a 1-to-1 ratio. So the molar amounts are the same. And for calcium carbonate, the molar mass is 56.08 grams per mole. Moles multiplied by molar mass gets you the mass. So my theoretical yield is 6.95 grams. Now this time, our calculation is going to be a little bit different because we already know what the percent yield is. We're trying to find what's the actual yield going to be. But we're going to start with the same formula. The percent yield is the actual divided by the theoretical. Now our percent yield is 92.4%. So I can write that like this. And my actual yield is what I don't know. So I'm just going to leave that. But my theoretical yield, I calculated it to be 6.95 grams. So now we got to do a little bit of algebra here. To solve for the actual yield, I need to multiply 0.924 times 6.95 grams. And now I can just plug that into my calculator, and I will get an actual yield of 6.42 grams. So this would be what an industry application would be. So in a factory, for example, when they're producing a chemical, they know how efficient their reactions are because they've been doing it a long time. So they can figure out if I put so many kilograms of my reactant into the machine, I know how many grams or how many kilograms of my product I'm going to get because they know the percent yield. Now, if you look on the second page of your handout, you're going to see this list. So this is different factors that can affect your yield. So I mentioned them earlier, but here's more of a description. So I'll just encourage you to read through this list. Competing reaction, reaction rate, purity of the reactant, laboratory techniques. And you can use this as a guide when you're thinking about what are some possible sources of experimental error in your future experiments.